In this video, we're going to look at how I created a object-oriented macro language on top of our C++ code base. For those who haven't seen any of the previous videos, we have a fairly large code base. About half of it is general purpose. The other half is a home automation platform called CQC that is built on top of that. And I will provide a link in the description. And we needed a mechanism for users to customize CQC. Most of it is done point and click, but for those who can code, we wanted to allow them to do that. And we also need a means for third parties to write device drivers so that they can integrate devices into CQC, and we don't expose any of our C++ interfaces, so we needed some other means to do that. We didn't want to use a general purpose language because we needed much more control than that, and we also wanted to keep it simple and safe. This is not for professional developers typically. First, let's just take a look at an example. This is called CML, our language, CIDLib macro language. And I'm going to, this is our CQC administrative interface. I'm going to expand out the customized macro section here. And these are just some testing macros. This is my development machine. So here's one here. We'll look at this one called num to num. And it basically takes a number as spoken and turns it into a actual number. And you can see it uses the kind of the common class path scheme that so many languages use to create a hierarchy of classes. You can import other classes. This is a standard runtime one. You could also import your own written ones. You can define types. Here we have a vector of strings. You can define enumerations, which are used a lot in CML. Actually, exceptions are enumerations in CML as well. And you can define literal values, members, and methods. And you can define a good bit of semantics, so you can indicate various attributes of blocks of methods, and you can provide input and output indicators on parameters and that sort of thing. You have a constructor as usual. You can have others, and you have a start method in this case because this is something intended to be called from the outside. So this is the equivalent of a main in a C program, and this one is taking a string to convert and is putting back out formatted in a string in this case because it's intended to be called from our action system in CQC. It is just the formatted number that results. And if something goes wrong, we get an error message here. So I'm just going to run through this really quickly here. I'll tell it to, well, actually, let me put a breakpoint here. So I'll tell it to go. And I need to provide the parameters. So let's say 155. And we just need placeholders for the others. The debugger in this case will provide output objects for those, but we need something here for parameter validation. So I'll just say outval and error message. Okay, so it runs up to the constructor so that we can debug through that. So I'll say go again. And so it runs down to our first line here. And you have all the usual things. So assignment, we have a method call here. So we can call a method on the string tokenizer to tokenize the incoming string. We get back out the count of tokens. We can look at class members and method locals. In this case, token count is a method local here. It says we have 5 tokens. Quality testing. We have compound equality testing. We have loops and that sort of thing. So all the stuff that you would expect, basically. It's a fairly full-featured language. So I'll just run it down to the end here. And we'll go again, and we'll step over this last 2. And if we look at the method parameters here, so on the input we had 155, and on the output we have the actual formatted 155. So it's a reasonably full-featured language. The limitations are single-threaded and single pass also, so there's no forward references. That allows it to compile very fast, and we need that because it's often invoked in response to the user pressing a button or something. So we can't have a big long optimization scheme or anything like that. And there's also no aliasing, so that drastically simplifies many things about it, and it also makes it vastly safer for non-programmers. Okay, so you kind of give a feel for what it can do. You can go back and slow that down and kind of read through what's going on here a little more if you want to after the fact. But let's actually look at how it's been implemented. So let's go look at the code here, and we're in the here in the general purpose section of the code base. And if we go down to language utils, this is the CML stuff, and we have an engine and we have a debugger. And what you were seeing just then was the debugger. It's an embeddable IDE that allows you to embed a compiler editor into editor debugger into an application. So we just embedded that in our administrative interface. What we're interested in here is the engine. And this provides the language parser, the virtual machine, the runtime classes, and various utilities. And it defines various interfaces that are used to allow the containing application to link itself up to this engine. So this is also an embedded engine, of course, right? So we can use this within any application. So let's take a look at that. And the most important thing here is the engine itself. And this is the kind of the core. Everything revolves around this. So first, let's just run down to the bottom and take a look at the data, which will kind of give us a feeling for what it does. We have a call stack, and CML, like many languages, is call stack based. And you can go look that up if you want to know what that means. But basically, when you make a call, you push it onto a stack, you push the parameters, you push the return values, those get messed with. And when you come back, you pop them back off. And so it's a context of where you are and what you're operating on at any one time. We have a list of all the classes that have been referenced. And these are the information classes. So let's start off here at the beginning just to say that for every class in CML, we need two classes to represent it. One is the information about it. So what methods does it have? What members does it have? Any literal values, all that kind of stuff. And the other is the actual value that represents an instance of that class at runtime. So we'll have one instance of the info class that gets stored here, and that gives us information about all the instances of that class, and the instances are stored elsewhere. They're stored as members of other classes and temporary values and all that kind of stuff. But basically, the deal is we have an info class and a value class for every actual CML class. We have a temporary pool here, which we use just to do things like if you want to do an operation on a number and you just pass a literal one value or something like that, we don't want to have to create something just for that. So we have a pool for kind of basic values, and we can just get one temporarily out, operate on it, and give it back to the pool. So that drastically speeds things up. And we have a debugger interface. The debugger is a cooperative one. It's not like a hardcore debugger like Visual Studio or something that operates using very low-level CPU sorts of functionality. It's a cooperative one, so the engine will call back on this interface when it's installed to let the debugger stop us and things like that. There's an error handler because we don't know how to deal with errors. The application needs to do with that, so we pass him errors. And there's a file resolver. All of the intrinsic and runtime classes are built into the engine, but any of your own that are compiled, we don't know where those are. So the application has to provide us with a file resolver to load those files. In the case of CQC, that's one that will go out to our master server on the network and pull down the classes to be compiled. So that lets this engine basically be independent of file system. And, it could be a file, it could be something coming out of a database, whatever, we don't really care. That's basically it. So let's take a quick look at kind of some of what this does. There are some various sorts of helper methods, of course. This one will invoke a default constructor for a particular class. We have here again checking various aspects of a class. All of the classes, methods, all these things are represented by IDs. So you will see lots of IDs passed around inside here. So this is the ID of a class to check something about. We have a lot of these types of things. So like B stack val at, C1 stack val at. So something is calling us and saying, look, I know that there is a cardinal 1 value at this index on the stack. Cardinal 1 in our case is as an 8-bit, a 1 byte unsigned value. So it's saying, I know there's one here. Please get it and get me out the value of it. And that just saves a lot of time over actually going and getting the value and checking it all the various places that we might want to do that. So for all of the fundamental types, we have these little helpers. And we can also ask that it be checked to be sure. At runtime, that's not really used. The debugger turns that on, and other things will turn it on as well. For the most part, for compiler-generated code, you don't really need this. This is like to add a class. So once the parser gets through filling in a class information object, remember we said there's one that contains all the information about an object, it will call us here and add it, and we'll give him back the ID that represents this new class. There's a deferred one here. Won't get into why that happens. We can find various things. So we can find a class by its ID from its class path. We can, let's see what else we got here. Get the current line, which is useful for logging. Some more get values on the stack. And there are various things for looking up stuff. Well, here's this runs the start method. So this is invoked once the containing application will do the parse, and then that returns. If that returns successfully, then it will call the default constructor, and then it will then, if that works, it will then call this, and that runs the start method. And this doesn't come back until the method is complete, or the whole thing runs. Right. We have various things for looking up stuff. So we're looking up classes by their class path or by their class ID. Some templatized ones here, like to get it and also cast it to its actual type and to test it if we wanted to. We don't do that here. This is to push a method call. So there can be a good bit of information involved in a method call. So this is a helper to say, please push this onto the stack, and it sets it all up correctly. So that's all the kind of stuff that's going on here. And this is sort of the core of it. It provides various things to manipulate the stack as well, and those calls are made as required. And to push here, these are to push various things onto the stack. Right? So that's something that's constantly being done: push things onto the stack and pop them back off again. All right. So basically, that's what we got going on here. So now, if we're going to create a class, we have kind of two sorts of separate types of classes. We have ones that are effectively just wrappers around C#, C++ code, and those are all of our runtime classes are just wrappers around the corresponding C++ class. So those obviously don't have any compiled CML. They are just a wrapper around another class. And then we have the compile CML classes, which do get compiled. Now they both share the same thing, that they have to have an information class and an instance value class. So those are the same, but the compile CML ones also have to have the compiled code as well. But first, let's just take a look at a wrapped one first and see what that looks like. Or actually, I guess we should first look at, say, the base class info class here. So this is what represents the information about a class. For the compiled ones, all of it's just added into data that's stored here in this object. So you can see these are things that the parser will call as it's parsing out our data and creating things. It adds them to. So it sees a literal, it gives us that to add. It sees a method, it gives us that to add. All of that stuff, an imported class, all of those things. So it's just loading up data on us. So that's where all of the actual class info is contained. And for a CML class, that's all that's required, just all that information stored away. So if we go to look down here at the data, there's quite a few kind of templatized classes created to store all this stuff. We can see that we have all the directives, the imports of other classes, literal values, members, methods, all that stuff. And in the case, if it's a CML class, we also have the compiled method implementations, right? So this is where all of the information that we need to run all the methods and everything to access all the members is stored. But it's not the actual object itself. That's represented by the value object. So let's look at that. And for a CML class, there's not much here. It basically is just it will be loaded up with all of the actual members. So a class has members, and those members have values. And so when the parser is creating the class for a CML class, it will just call us and just tell us to add all of those members to ourselves. So for a CML class, this is all that's really needed as well. We don't need any derivative of this or anything. We just need the list of all of the members, which is here. All right. Now for a wrapped C++ class is kind of considerably different. So let's look at one of those, and we'll look at, say, like at one of the COM things here. This is for serial port stuff. So here's one for a COM port configuration class. So in this case, we have to do a derivative of the value class because we need to store extra information. We need to store a C++ object that we're going to operate on, which we do here. So we just gin up one of our COM port config objects and store it here. And we own this, and we clean it up when we go away. Here we just expose that object for use, and here we just provide some common support stuff that all value classes need to provide. So we can, this supports the debugger to format out values for display. This is to support copy construction, right? And down here, this is where kind of the meat of the wrapped ones are. So this is the info class for this particular com-config guy. And in this case, because it's not being loaded up from CML itself, not being parsed, we have to do that ourselves. So we have a bunch of IDs where we define our methods, where we define our types, and then we store the IDs to those guys. And we have to do that ourselves in this case. So let's look at that. So here's the value object. We just store we gen up an instance of the config guy and keep it around and expose it for the info class to operate on. So the info class, we initialize all of our pointers. We call our parent class info class, and we say, this is our class path. This is our name. This is our parent class path. This is we are copyable. It's a final class, etc. This is our parent class. And here we initialize all of our stuff here that we're going to fill in. So then when the engine calls us to initialize this, we have to create all this stuff. So for the data bits type, we create an enumeration info object, and we set it up, and we tell it has 5 values, and we just load them up. So we're adding a value for each enumeration value that this enum can have. And in this case, what we're doing is we're actually setting the ordinal to the underlying C++ value. So that means that they always stay in sync. We don't have to worry about that or do a translation or anything. We know that the value equals the C++ value for these. Once we get it set up, then we do an initialization on it, and then we can add it to ourself, or we can add it to the engine as an available class, and we store the ID, and then we add it to ourself as a nested class. And we do the same for all those other enums that we looked at, or that we contain. Then we can define our methods here. And so for each one, we just define a method info object, and we give it a name. We say, this is the return value. Is it public or private? Is it final, non-final, required, override, all that kind of stuff. And then if there are any parameters, we tell it about any parameters. In this case, it's one of those types we defined above, the port flags enumeration. And then we add it to ourself as a method, and we get back the ID. And this is what we'll use later to call it. And all the rest of them are just like that. Okay. So if we go down here to where one gets invoked, so when one of our methods gets invoked, the info class is called, and the instance object is provided to it. So this is all of the actual functionality is provided in the info class, and then we just operate on a particular instance. And we also get the method object that we're being asked to invoke as well. So what we do is we cast that instance object to our actual type, our actual value type, which is a com-config value. And then just for convenience, we get out the comport object. And then what we do is we ask the engine, what is the first parameter index on the stack for this method here? And then we store that, and everything is relative to that in here. And we get out our method ID. So then we just say, okay, well, is it this method? Is it this method? Is it this method? And whichever one it is, we run that one. These are not compile time constants, so we can't do a switch statement or anything. We might come up with something fancy smancy to do here, but haven't bothered with that so far. So let's just look at a couple here. So for this is clear a port flag, and if we were to go back up there and look, we would know that we get one of the enumerated values for a port flag, and that's the one to clear. So we tell the engine, we know that there is a value of an enumerated type at the first parameter index. So please get that for us. It'll check it for us. And then we get back the value object. And then all we have to do is just basically call that and pull out the actual value of the enumeration, the ordinal value for that enumerated value, and we use it to turn off flags in the config port. So we just and them with the not of the actual flag value, which is the usual way of turning off a flag in a bitmap thing. And then we just cast it and send it back in. So that's pretty simple. So for one of these other ones here, like this is a get, And by our calling conventions, the return value, if there is one, is at the first index minus 1. So we get the first index minus 1. We tell the engine, hey, I know there's a card for value there. Please let me get access to that and check it for me. And then we get that back, and we just turn around and set its value by getting out the baud rate from the port config object. And that's more or less how most of these wrap classes go. Some of them are more complex than this, but not very much so, because really we're just wrapping existing functionality, and all we're mostly doing is getting values out of CML world and into C++ world and vice versa. All right, so that's what most of them are like. Right? And so let's go ahead and take a look at the thing that we haven't looked at so far, which are the actual CML compile classes. And we do need a value. We do need some derivative of the value and info base classes, because those are not concrete classes. But we don't really need to store anything in them, because, as we said before, everything is already stored there by the parser in the base classes. So we just create some basically empty placeholders. So we have a standard class value, which derives from the base class value. And then we have a standard class info, which derives from the base class info. And they don't really do anything but just override the absolutely necessary stuff, and that's it. So for this guy, all we do is override the factory object to create a new instance, and that's all we do here. Everything else is just the information that the parser store down here in the base class, right? So there's not much to these guys. And in some cases, like if a C++ wrapped class doesn't have any actual C++ code that it needs to track, it'll just use one of these value objects here as well. It needs to do something, and this is as convenient as anything else. There's nothing special about this one, so he just wraps one of those guys. Right? All right, so let's look at the one thing that we haven't looked at here, which is the where kind of the metal meets the road, or the pedal, or whatever that saying is, which is the compiled content. So in those cases where it is a compiled CML class, then we have a method impl, and that is the compiled code. So for each of the methods, we will get an instance of this stored in the class info class. So in this case, when the class info is asked to invoke a method, it just looks up. Well, let's go look at it here. So this is the standard class stuff here. Oops, I must have closed that. So if we go to the standard class and we go down to where it gets a method invoked, all it does is it says, find the method impl for me. If it's not there, we return false, say we don't implement that. And if it is, it just calls invoke on that method impl, right? And that passes in the instance value that it should operate on and the actual method to invoke. So that gets us, so when we do that, that gets us over to, I keep losing my classes here. I don't particularly like the way this editor manages the list there. Anyway, so if we go look in the method impl CPP file here, I'm going to skip down over a bunch of bookkeeping stuff there. So what happens is it calls invoke on that, and this is a derivative of the method impl that is specifically for opcodes. And I guess we could look at that really quickly here if we go down here. So we have this this is the basic method impl, and we have a derived class from that for opcodes. And if we look at that, we see that we just have a vector of opcode objects. So these are the actual opcodes that the compiler generated when it compiled the code. And so when this method gets invoked, we just start at the 0th opcode, and then we just process them, and that jumps around as necessary and as we run the various opcodes. So let's look at that. So we come in here to the invocation. We basically push any locals. So if there's any local variables, we need to get those onto the stack. And then we just set an instruction pointer to 0, and we enter a loop down here until we're done. So we get the current opcode at the current instruction pointer, and then we do a big switch statement, and based on the particular opcode that we are running, we will do this, that, or the other. These are considerably higher level than what you would get in a language that is compiled down to actual CPU opcodes. We have a few things that are similar, but mostly these are far higher level. So here we have all of the calls, the things that can call a method on something. They're all very similar, so we handle them all at once. And based on the type, we just kind of set up the stuff that we need. And then we basically get down here and we just ask the engine, push this method call for us. That sets up all the stuff on the stack that's required. And then we just invoke the method as we just were looking at before. We say, please run this method. If this is a wrapped one, then it gets handled in the wrapped sort of way. If it's a CML compiled one, it gets handled in the CML compiled sort of way. All right, so let's look at some other opcodes here. I'll just pick some at random that might be interesting. So this is a copy constructor. It says, well, there must be two objects at the top of the stack. They have to be the same type, and they both have to be copyable. And then it will just call the copy from to do the copy constructor, and then it pops them both off. Right. And then let's see, look at some others here. This is a conditional jump. All these jump sort of things, what they do is they figure out, do we want to jump? If they do, they store some immediate value into the instruction pointer. And then the next time we come back around to the top again, this is now pointing to some other opcode, right? So, of course, the compiler calculates all these correct jumps and everything. There's an end of a try block. We get everything cleaned up. This will flip the two top value objects on the top of the stack, which is often convenient. This is one thing we do ourselves here, the logical operations. This is more like what you might, closer to what you would have in a real compiled language down to CPU instructions. So we say, okay, there has to be two values at the top of the stack, and they both have to be Boolean values. So we call stack value at to get a Boolean value back. And then we do the logical operation. We pop the two guys off, and then we push a temporary back onto the stack that has the result. So that's a very common sort of, stack-oriented language thing to do. And this is similar. We negate the thing at the top of the stack. It has to be a Boolean. We negate it, pop it off, then we push a temporary Boolean back that has the value. So anyway, that's all it. I mean, so effectively, we just run around this loop until we either fall out the bottom, or we see an exit type of or return opcode. Here's some that are for pushing immediate values. So these are just so if you did say like push 8 or something like that. So we would just push an immediate value out of the pool. These all get pool values and push them onto the stack. And eventually we will come to a return, hopefully, or we just fall out the bottom. That cleans everything up and we fall out. All right, so I mean that is basically what's going on here. There are various others, but there aren't really that many, opcodes in this thing. Nothing compared to a real CPU, which could have like hundreds of them. But they're quite high level, and they're very specific to the language in some cases for our needs. So at the bottom we say, did they do anything special? If not, then we'll just bump the instruction pointer to the next. If they did do something special, then we don't bump it. They already set it, so it was a jump instruction or something like that, and we just keep what's already there. And if we're at the end, then we hit the end without actually getting a return, and we just break out. Okay, so obviously that was sort of a whirlwind tour. You can slow this down and look at stuff at your leisure and pause it and check things out. But it's, as software things go, it's not insanely complicated or anything. I mean, it's not trivial, but it's not crazy. Writing a good parser is a little tricky, but it's not terribly hard. And once you kind of learn those skills, you can apply them in a lot of different ways. But the bulk of what is in here is that stuff we just looked at, plus a bunch of C++ wrapped runtime classes. So all this stuff for arrays, ASCII, async HTTP, base64, all that stuff, cardinal classes, those are all just wrapped C++ classes. So there's not a lot in them. And basically the rest of it is mostly the stuff we just looked at, and the parser. There's a good bit of stuff in the parser here. It's not crazily complicated. And it's quite a nice little language. It's served us very well, and it's quite robust because it makes it very difficult for you to shoot yourself in the foot. There's no threading, no aliases, no forward references, any of that stuff. So it's very safe, which is an important thing for an automation-oriented language. Maybe if anyone's interested, we could dig into some other specific details, but basically that's the gist of it. And so in order to keep this from being 10 years long, I'm going to stop it here, and we'll see you in the next video.